Now we will do practice problem 2.1, and this problem asks for we are given the op-amp in the inverting configuration, and we're told that R1 is equal to 1 kilo ohms, R2 is equal to 100 kilo ohms, and the closed loop gain, if you recall, is the gain from V in to the V out. If it was ideal, if this was an ideal op-amp, it would be negative 100. But the question asks for the op-amp is not ideal, so A is no longer infinity because the op-amp is not ideal anymore. It's a real op-amp. Now A is limited to 10 to the third. So now we're asked to find the closed loop gain if A is 10 to the third. We're also asked to find out what is the percentage error of the closed loop gain compared to the ideal case. And then finally, we're asked to find out what is the voltage at the inverting terminal if V in is fed with 0.1 volts. So recall that the inverting terminal is the voltage here. So we're asked to find out these three things. So first, let's find out what is the closed loop gain. So we can just use the formula that we derived earlier. So this is the formula that you use to calculate the closed loop gain when the op-amp is not ideal. So we can just plug in the values. So R2 is negative. Okay, R2 is 100 kilo ohms, R1 is 1 kilo ohms, and the denominator now, so it's 1 plus R2 divided by R1, everything divided by A, which is, we're told that A is 10 to the 3. Let's solve for this. So this 10 to the third cancels, 10 to the third cancels. What we are left with, negative 100 in the numerator. The denominator is uh, 1 plus 100. Okay, so 1 plus 1 over 1 times 10 to the third plus 100 divided by 10 to the third. So this is equal to negative 100 divided by 1 plus move it 3 decimal 1, 2, 3, so 0.001 plus 0.1. Okay, so that's negative 100 divided by 1.101. So the closed loop gain in the real op-amp is, you go look at some calculator. Oh, 1 plus, yeah, 1, oh. So there's a small addition here, is 1 plus 0.1 plus 0.001 here. So now it's using calculator. Negative 90.8265. This is the closed loop gain from the real op-amp. So just recall that remember that just V out divided by V in. So now we're next question asks for what is the percentage error. So we're comparing the closed loop gain in the ideal case is this value here. Compare that to the compare the compare the gain in the real case here compared to the ideal case of negative 100. So to calculate percent error, the calculation is you take the ideal, then you minus the actual, you divide this by the ideal, you put this in absolute value so that it would be a positive number, and then you multiply by 100% to convert the decimal into a percentage. So if it was ideal op amp, it would be, the closed loop gain would be negative 100. Now we calculated that the real closed loop gain is negative 90. You divide it by the ideal, and then you multiply by 100%. So now we'll just use calculator, and percent error is 9.174%. Then there's one more thing they're asking. It says what is the voltage at the inverting terminal. So the inverting terminal is this terminal here. So what is the voltage there if V in is fed with 0.1 volts? That's the question. So the same relation will always hold, is that V out for the op amp. So V out for this op amp is equal to open loop gain A times V plus minus V minus. This is always the case. Now the V plus, which is also called the non-inverting terminal, it's connected to ground, so we can just put a 0 here. So now we see that V out is equal to negative A times V minus. If you solve for V minus is equal to negative, okay, let me add another point to say is that closed loop gain is so closed loop gain refers to V out divided by V in, right? So V out is equal to closed loop gain G times V in. So you can plug this to here, then you will find out that G times V in is equal to negative A times V minus. Again, the objective is to find out what is the voltage at the inverting terminal if V in is fed with 0.1. So now we can find out that V minus is equal to negative G times V in divided by A. So just plug everything in. G was negative 90.8265 minus a negative becomes positive times V in. We're told that V in is 0.1, and then A is 10 to the third. So we just use calculator, and that is so it is 9.08 times 10 to the negative third, so millivolts. So now we will look at another problem. We'll look at another practice problem. Oh, actually, V in was 0.1 volts, so there is no it was not multiplied by a negative number, so okay, yeah, V in is 0.1 volts. Okay, yeah, 9.08 millivolts. Okay, So now let's do another practice problem. We're going to repeat the same problem, but for now we're looking at a is equal to 10 to the 4th this time. So we can just use this same thing again. I'm just going to reuse it, just put -100, that -100 on the top, and then I'm just going to do 1 plus yeah, let's just plug everything in, but let's also simplify at the same time. Okay, if I use calculator, so if I use the calculator, then the g is equal to -99. Okay, let's do the percent error calculation again. It is just like the ideal, which was -100 minus the actual -99 divided by the ideal -100 times it by 100% to convert decimal into fraction. If I use calculator, so this is just cancels, then you'll get 100 minus 99 is just 1, so that's 1%. Okay, so now again the question was asking in the problem, solve for V minus, which is the inverting terminal, if the V in is 0.1. So we'll just reuse the same formula as before. I'm not sure if there's a negative sign here because it's just the Vn times Vout. Okay, so it's -99 times it by V in 0.1 divided by 10 to the 4th. If I use calculator, the voltage at the inverting terminal is it was times 10 to the 3rd. Yeah. Okay. Now let's repeat it one more time for a is equal to 10 to the 5th. So in order to save time, let's just plug in everything again. His inside stays the same. Okay, I use calculator. Well, if I use calculator, it says that G is -99.899. Okay, percent error is ideal minus -99.899 divided by ideal times 100%. I have this written down is 0.1%. And lastly, V minus equal to G times Vn divided by A. So we can plug in G times it by V in divided by A is equal to negative 99.99 microvolts, I think. So the point of this exercise was to summarize into table. So we're just going to make a table here. We did 3 practice problem. First we solve for A as 10 to the 3rd, then we solve for A as 10 to the 4th, then we solve for A as 10 to the 5th. And the gain in the first case was negative 90.82. In the second case, negative 99. In the third case, negative 99.9. And the percentage error in the first case was 9.17. In the second case, it was 1%. And in the third case was 0.1%. And also the V minus in the first case was 9.08 milli. In the second case it was negative 0.9 milli. And in the third case was negative 99.99 micro. So what is this? Let's make some observation here. So we're changing A quite drastically. First we solved for 10 to the 3rd, then we solved for 10 to the 4th, and then we solved for 10 to the 5th. So we have made some pretty drastic change every time. Multiply by 10 each practice problem we did. But look here, you're going from, so you're multiplying A by times 10, but here it's not really changed much. It's just the gain is not changed a lot, so it's not changing much. And likewise, this percent error, it's like this rounds to 10, right? And then this is 1, this is 0.1. So the percent error is scaling with A linearly, but G does not change much. Also, remember that as A goes to infinity, so as A gets higher, going to infinity, we're making the op-amp more and more ideal, right? So you can see that if it was ideal, the 2 terminals of the op-amp would be at same voltage, would be grounded. So you can see V minus is slowly approaching 0, right? So it was, I think it was, forgot to copy the minus sign there. So it was 9 millivolts, then it became 0.99 millivolts, then it becomes 99 microvolts. So it's getting closer and closer to 0, the virtual short. So as the op-amp becomes more ideal, the inverting terminal approaches virtual short. In this case, the virtual short means virtual ground, because if it was ideal, this would be 0 volts, this would be 0 volts. problem 2.5, oh sorry, 2.1b. So we had solved for A, now let's go to part B. It says open loop gain A changes from 100,000 change to 50,000. So we just cut in half. So the question is, what is percent change of the closed loop gain, G? So to solve for this, we see that it's going from 100,000 going to 50,000. So let's do the old value of closed loop gain. As we recall from earlier, the formula that we derived to calculate closed loop gain for the ideal, non-ideal op-amp, which is the real op-amp, is this here. So we're told that R2 is 100 kilo ohms, R1 is 1 kilo ohm. $100 divided by 1, the kilo ohms cancels out. Okay, so 100 kilo ohm divided by 1 kilo ohm is just 100 divided by 100,000, which is the A. So, oh yeah, okay. If I use calculator, it's negative 100.099. Now we're going to plug in a different value for A this time, for the new, which now becomes 5E4, which is 50,000. If I use calculator, I have written down that it's negative 100.19839. So let's find what is percent change. So percent change, it is like you do the new and then you minus from the like the old, and then you divide it by the old, and then you multiply by 100% to convert the decimal into a fraction. So the new is like this. So if I use calculator, I will find out that the percent change I have it written down is 0.092917%. So that's like 0.1% change. So what is the observation that you can make is that I'm cutting the open loop gain cut in half, but I only see a 0.1% change in the closed loop gain. So we cut the open loop gain by half. We cut in half. But G only changed by 0.1%. So in other words, changing the open loop gain A has little to no impact on the closed loop gain G. So the conclusion that we draw from this is, even though the op amp is not, from these two exercises, we have discovered that even though in the non-ideal op amp the gain is not infinity, but rather the open loop gain A is not infinity anymore, but becomes a finite number. But this does not have a huge impact on the actual closed loop gain. So this is a very powerful concept, because the closed loop gain depends more on the values you select for R2 and R1, depends on that more than it depends on what is the open loop gain A.